Couple of things to notice about the question. It states there is a large excess to the bromoalkane, so that means it is essentially constant. And the other thing is that they give you the concentration and time, but they don't give you the final rate. They're asking you to work out the rate here. However, you know that rate equals change in concentration divided by time, so by doing the division you should be able to get 5.7 times 10 to the minus 5. Then in terms of determining the order, you're looking for comparisons between changes in concentration and changes in rate. So first of all, looking at the order with respect to C4H9Br, that must mean that your C4H9Br is changing, but the concentration of the OH- is constant, so we're looking at these two experiments here. Your concentration here doubles, and your rate also doubles. For our other reagent, the OH-, we're looking now for somewhere where the C4H9Br is constant. If we look now, the change in OH- actually has no effect on the change in rate, so that means it is zero order with respect to OH-, but as we said, first order with respect to C4H9Br. From this information we can now work out the rate equation. Don't forget to put your K in, you always have to include the rate constant, and we know that it is just C4H9Br. We do not include the OH- because anything to the power 0 is equal to 1. Now using the rate equation that you have worked out, rate equals K times your C4H9Br. You can rearrange this to find K, so K is equal to rate divided by C4H9Br. You can use any of the experiments in the table on the previous set, and if you substitute in the numbers you should find that you have a value of 1.7 times 10 to the minus 3. It also asks you to work out the units, so don't forget to include this in your answer. For the units, you just look at the units of rate and the units of concentration. So if K is equal to rate in moles per decimeter cubed per second, the change in concentration per second, and your concentration is given in moles per decimeter cubed, then all that happens is your moles per decimeter cubed cancels with your moles per decimeter cubed, leaving you with seconds to the minus 1 as your units. What evidence supports the theory that there is more than one step in the reaction mechanism? In our rate equation, the only chemical from the reagents is our C4H9Br. That means that the OH- is not included in the rate equation, so that means it is not in the rate determining step and therefore must appear in another step, i.e. there is more than one step in this reaction. In terms of the mechanism, we only have one molecule of C4H9Br in the rate determining step because it is C4H9Br to the power 1 in the rate equation. If there is only one molecule in the rate determining step, then that means it is SN1. That means that the carbon-bromine bond will break, leaving you with a positive carbocation. The OH- will then be attracted to that positive carbocation. Negative is always attracted to positive, and that will give you finally your COH bond. You should draw in the rest of the bonds as well. If we had an SN2 reaction, that would be where we had two molecules in the rate equation where the C4H9Br and the OH- appeared in the rate equation. The SN2 reaction then would be where the two molecules in the rate determining step react, and it would be your OH- attacking the slightly positive carbon being slightly positive because of the difference in electronegativity, and then the reaction will proceed along the SN2 route. This is an orders by inspection question. It's asking you the order with respect to oxygen. So that means that your oxygen changes, but you need the nitrogen monoxide to stay the same so it doesn't have an effect on the rate. The change in oxygen is that it has doubled, and if you look at the rate has also doubled, so that means that the order with respect to oxygen is first order. Whatever happens to the concentration, the same thing happens to the rate. For your nitrogen monoxide though, this time you're looking for the nitrogen monoxide to change and the oxygen to be constant, so comparing 2 and 3. When the nitrogen monoxide doubles in concentration, the rate actually quadruples. So any change in concentration has a squared effect on the initial rate. That means it is second order with respect to nitrogen oxide. From the orders by inspection, we can say that rate equals K, always include your rate constant. We've said that the order with respect to oxygen is 1, so we leave that as that. And we said the order with respect to nitrogen monoxide is 2, so don't forget to put the 2 at the top. Calculating the rate constant means that we said it K equals rate divided by oxygen concentration times by the nitrogen oxide concentration squared. Don't forget the squared part. When you substitute in the values, that should give you 652.8. You can use any of the experiments in the orders by inspection set of data, just use them all from the same experiment. For the units, it will always say include units. You just take the units of the rate and the units for the concentration and use that to work out the units of K. Rate is always moles per decimeter cubed per second, the change in concentration per second. On the bottom we've got moles per decimeter cubed for our oxygen concentration, but then we have moles per decimeter cube squared, so actually we have moles per decimeter cubed twice for the nitrogen monoxide. That means that one of the moles per decimeter cube cancels out, but we're still left with 2 moles on the bottom and 2 dm to the minus 3. If you want to show that, instead of having the dividing line, you can actually show mole to the power 2, because we have 1, 2 of those, dm to the power 6, and still seconds to the minus 1. Your moles should be to the minus 2 now, because they were to the positive 1 on the bottom. Your decimeters is to the positive 6, because it was to the negative on the bottom. And seconds is still to the minus 1. Those are your units. This question is asking you to write the equation for the overall reaction. If we look at what we have here, we have 2 NO2 turning into 1 NO and an NO3. But the NO3 is actually used up in the next step, so we would not include that in the overall equation. You are then adding 2 COs, making another NO and 2 CO2. So the overall equation is 2 NO2 plus the 2 CO from the second step, which will turn into not 1 but 2 NOs, 1 from each step, and your 2 CO2s. Just double check that that is balanced. In this case it is, so that must be the correct one for the overall reaction. The question tells you that the overall reaction is second order. Suggest a rate equation. You know that you can use your rate determining step reactants to work out your rate equation. In this case, rate equals K, because we always include the rate constant, and we use the reactants of our slow step, so we have NO2 as the reactant, but we have 2 of those, so it is NO2 to the power 2. That indicates that there are 2 molecules of NO2 in the rate determining step. The important part to notice about this question is that it states that these are in large excess, the propanone and the hydrogen ions are in a large excess. That means that we can say that these are essentially constant and therefore will have no effect on the rate. That means it is only the iodine concentration affecting the rate, so that means we can work out the order with respect to iodine. Be careful that you are specific and say it is the iodine concentration rather than just the iodine. You need to be specific. If we now wanted to work out the order with respect to propanone, we would have to change the propanone, and we would also have to monitor the effect that changing the propanone concentration would have on the rate. Things that we would expect to see if this was order 1 would be every time the concentration doubled, the rate would also double, so we have a proportional relationship in terms of the change in concentration and change in rate. We would also expect any graph of concentration against time to have a constant half-life. So it would be a curve and you would have a constant half-life, sometimes referred to as T, a half. The next question asks about why the minimum number of steps in the mechanism must be 2. For this we need to look back at our rate equation. Our rate equation doesn't actually have I2 in it, it's to the power 0, so anything to the power 0 equals 1. So we can say that the I2 does not appear in the rate equation. If I2 does not appear in the rate equation, then that means that I2 does not appear in the rate determining step. If I2 as a reactant is not in the rate determining step, then that implies that there must be another step in the mechanism. Interestingly, H plus does appear in the rate equation but does not appear in the chemical equation. This must mean that it is a catalyst. The question asks for the ionic equation, so do make sure you have the ions in there. The relevant ions are HCO3- and H+, reacting together to give you H2O and CO2. They will allow HCO3- and H3O+ to give you 2 H2O and CO2. They will also allow H2CO3. However, I would say it's better to give the H2O and CO2 as the products, because this is a carbonate reaction with an acid, which will give you a salt, water and carbon dioxide. This final question is actually the triiodomethane reaction from the organic part of Unit 4. Your propanone CH3COCH3 will react with iodine under alkali conditions, NaOH, to produce the salt CH3COONA, and you will also have sodium iodide, and you will have some water produced as well. You do need to balance this as well. You should have 3 iodines, 4 sodium hydroxides, 3 sodium iodides, and 3 waters. As I said, this is the triiodomethane reaction. This question is referring to titrometric analysis, where you use titrations to analyse the concentration of the reaction mixture at certain points. By reacting with sodium hydrogen carbonate, you neutralise the acid catalyst and effectively stop the reaction. They'll sometimes say it quenches the reaction. If you note the time that you stopped the reaction at and the concentration at that time worked out from titration, you can then begin to draw a concentration time graph. From that concentration time graph, you can use a tangent to work out the rate and produce a rate concentration graph that can tell you the order of reaction. this is quite a common example, that iodine and propanone. Because you have iodine, a suitable indicator to use would be starch. In part C, you have propanone and acid at 1 mole per decimeter cubed, whereas the iodine is only 0.02. That means that your propanone and sulfuric acid are in excess. If they are in excess, then we can say that that means they are virtually constant and therefore will not affect the rate. That means that as you change the iodine concentration, any effect on rate is only due to the iodine. This is a common question that comes up in terms of discussing having an excess of a chemical, meaning that it will be constant. In this question, you are given the volume against time. That's the same as saying you have concentration against time, essentially. Here, you use the gradient to work out the rate. If we have a constant gradient, we have a constant rate. So as the volume is changing, as the volume is decreasing over time, the rate is staying the same. That means that as concentration changes, there is no effect on rate, so this is a zero-order reaction. For a measuring cylinder, we can say this might be quicker and allow you to do a variety of volumes because it has the different measurements on the side, and often they're made out of plastic, so you could say they were unbreakable. However, the advantages of using a pipette are that they are more accurate or more precise, and they allow you to extract samples. For example, in our titrometric analysis, when you take a sample out of the reaction mixture to quench, to stop, and to then continue and do a titration with. The reason why water is added is to keep the volume constant. Here we have a total volume of 32. Here we have 10 plus 8 plus 10 plus 4, again 32. Here we have 20 plus 4 plus 4 plus 4, again 32 total volume. This means that the concentration is always proportional to the volume. Using the data to work out the order of reaction with respect to propanone and hydrogen ions, first of all looking at propanone. If we want to know the order with respect to propanone, everything else must be kept constant and only the propanone must change. That means that we need to look between experiments 1 and 3. Between experiments 1 and 3, the acid is constant and your propanone concentration has halved. If we look at the rate, that has also halved, so the change in concentration is proportional to the rate, so that we can say for propanone it is first order. If we now look at where our H2SO4 is changing, but our propanone is constant, so between experiments 1 and 2, when our H2SO4 is halved from 20 to 10, our rate is also halved. So we can say with respect to the hydrogen ions, with respect to the H2SO4, it is also first order. This means that our rate equation is rate equals K for the rate constant, multiplied by our propanone concentration, CH3, COCH3, first order, so it's only to the power 1, multiplied by our H plus concentration, again to the power 1.